Jim Simonelli 先生将为我们带来题为“电力及算力：规模化打造未来 AI 资料中心”的精彩分享。For our next session, it is our great honor to welcome our speaker, Mr. Jim Simonelli, SVP and CTO at Schneider Electric. Mr. Jim Simonelli will share his insights titled Powering the Future with Scaled AI Data Centers. Ladies and gentlemen, please welcome Mr. Jim Simonelli.
你好. Good afternoon. Boy, that's a long walk at the end of the day. And I appreciate you showing up to this session. I know it's the last of the session, but I guarantee you it's going to be the most exciting. Or I guess maybe that's my job, is to ensure it is the most exciting. But I can tell you it's an exciting topic. It's a topic that I am enthusiastic about, and at Schneider Electric, we live, eat, and breathe these topics all day, every day. So you may have noticed that I changed the title a little bit. You know, I talked about scaling AI data centers, and I really talked about kind of the new era that we're joining. And no, you're not misreading the title here. This is not about the megawatt era is not going back to the 90s where we used to build 1 megawatt data centers, used to be big. That's just not the case anymore. We're talking about scales of gigawatts now and today, but I wanted to be clear that the era that we're entering in is the era that is the 1 megawatt rack, and not just doing it by doing it at scale. And I kind of want to use that theme to kind of talk about what are the challenges with this to certainly scale it efficiently and effectively, but also sustainably. So that's kind of the narrative that I want to go through today, is not just kind of scaling for the sake of big gigawatt numbers, but also how to do it effectively with purpose, and ensuring that it can be done without disruption, and ideally with a future-proof model in mind. So that's my mission for the next 20 minutes or so, and I'll let you check me at the end to see if I actually satisfied that mission. Sound good? Sounds good. All right. So look, before we talk about anything specific, I do want to step back and think more holistically around what are the themes that all data centers need to consider if they really want to scale in a sustainable way. And we try to break them down into 3 big themes. It's not that hard to conceive, but in general, you want to build them dense. You want to build dense because generally you get more better capex and dollar per megawatt perspective. Generally, the more dense you make things small, you get the less overhead. You get a better performance on the capex side. However, as you just heard from our SambaNova friends, and also from what you see at GTC, is that the more dense we pack our compute, the more effective we are in terms of token production, which is really the notion of data centers. So run dense is a key theme for all data centers to be sustainable, effective, and efficient at scale. The next has to do with heat rejection. This is around running hot. We know that we can improve the efficiency. The single most inefficient element in data centers today is in heat rejection. So therefore, if we run hot, we can use less mechanical cooling systems, become more efficient, which means that in a power-constrained world, which is the world we're living in today, every watt that comes into the data center is available, can get right to compute, to create tokens and drive revenue. So that's why running hot is a theme that runs across the day. And the last one may be less obvious, but data centers, like if they really were 1 megawatt or 10 megawatts, this probably wouldn't be a notion. But at a gigawatt scale, or by clustering tens or sometimes dozens of data centers of 200, 300 megawatt sizes all in one network of the grid, is that running steady becomes a key element as well. And this is really the notion of enabling sort of the grid reliability that's required, and ensuring that any variations, ramping up and down of loads, or fast variations of loads, they do not interfere with the local grid, and actually can be more of an asset for the grid than they can be for any other aspect of the grid space. So run dense, run hot, run steady, run dense. I'm going to click into a little bit more in this presentation. This is largely around thinking about, hey, I'm running dense, but what's the load size? What's the block size of my compute? You know, is it 2 to 8 megawatts is a good number today? Historically, we've always built kind of less in the 2 megawatt critical load. We see that moving up a bit, and that's, you think differently about density in that space. The availability trade-offs when you start running dense are really 3 nines or 5 nines. That has an impact on the cost effectiveness of that data center. And the last one, which I'm going to spend more time on, is as you run dense, you get power levels up above, say, 250, 400 kilowatts. There really is a requirement to change the supply voltage, just even for the IT rack to 800 volts DC. Those are all elements of what we mean when we say run dense. The next element of run hot really, again, as I said, is on the cooling side, but it really means thinking about how can we supply and reject heat from these chips, but at the highest temperature possible. 40, 45 C is kind of where things are moving today. What's nice about that number is it does ultimately provide return temperatures that you can almost reject without mechanical cooling anywhere on the planet. Now, there might be times where you might have that as a backup, but generally that is a very valuable thing for efficiency. It also means that we can also, again, so therefore you can use high temperature heat rejection with that space, but also it means that we get into the error where it may not be just around heat reuse. It could be about heat recovery, turning heat into electricity with advances of the technologies that are coming as well. It still is a little bit too low grade heat at these levels, but it's very, very close to being a useful heat component as well. In running steady, specifically, really what that means is when you're thinking about the ANI training and the power fluctuations that can cause, is that the role of UPS or 800 volt DC converters coupled with storage play a key element to ensure that any of those variations do not make it back out to the grid, and therefore the grid can remain certain and stable in that space. The other side is the opposite problem. And this is the problem of when you have clusters of large data centers. It's not uncommon to have 3 gigawatts of data centers load on a single transmission network. Any small perturbation on the transmission network could be a surge arrestor load. It could be only for several cycles. All of that 3 gigawatts goes off the grid and may not come back instantly. That actually causes a lot of stability problems with the grid. Therefore, new standards and compliance that are emerging to allow for that type of ride-through capability of large data centers as well. All these, running dense, running hot, running steady, are not just slogans. They're actually architectural principles for how we try to think about building data centers at scale, but in a sustainable way. So I want to just kind of make sure that that is the background theme through all of this. Scaling at speed means thinking about these 3 elements throughout the whole development and design of data centers moving forward. Good? Good. So now I want to think a little bit more about one problem that I face all the time, which is this notion of 800 volts DC. And I have a challenging problem to do right now because I want to do 2 things that contradict each other. The first thing I'd like to do is I want to try to simplify a complex problem to make it have a more holistic and clear conversation, so not just around like, oh, it's 800 volts, I don't know what to do. But I also want to make it clear that you have to think about this. It's not just as simple as, oh, it's a new converter, it's an SST if you want to lose those words, or a new type of solid state circuit breaker. It is a more complex topic than that. So I'm trying to simplify and also explain some of the complexities that are really kind of engineering problems that the industry and Schneider Electric are leading today. And to do this, we created a white paper. White paper 213, you'll see a reference to this at the end, but the way we tried to do that is kind of break the problem into 5 tractable elements, or 5 practical tractable principles. The first one is really, you'll see in a bit around the portfolio, is that 800 volt DC is not a single architecture. If you've been in the industry, you recognize that data centers, if you walk into a colo, a hyperscaler, someone that's more retail, wholesale, they all have a little bit different architectures and different principles of their designs. That doesn't change with 800 volts DC. There is still variation in that space because they're trying to tune themselves for different types of problems. Principle 2 is that in this role of 800 volts DC, we cannot take protection and distribution for granted. Selectivity and safety are equally important. And thinking about that as one of the key elements in concert with the load flows is another key element to think about. And it has some engineering challenges that are being resolved as we think about this, but it's not just conversion. The third is everybody who's in the industry today thinks about data centers. You need to continue to think about this holistically. It is largely around how does availability impact your architecture, because decisions made at the IT side change a lot as how you might think about where you put storage or not, what types of converters you might use, what type of redundancy schemes you might use. You have to think about these holistically, not just as one point by point. The last two oftentimes don't get enough attention. Principle 4 is understanding that sometimes the best technology does not win. Because remember, the principle of this was scaling and scaling efficiently, which means that it has to be ready to build in the gigawatts of gigawatt scale, and therefore capacity supply chain really has to be taken into consideration when we think about what is the right architecture for today and tomorrow. And the last one I will leave you with on principle 5 in the white paper is really thinking more about the notion of what happens when you stand this up. Operation and maintenance, particularly on things that are kind of new, 800 volt DC, in the procedures, those all have to be kind of written in and put into place, whether it be robots, drones, or humans, all have to understand what are the right procedures. So this is what we talk about of, if you break them down to these areas, it becomes a tractable problem. And it's something that can be resolved through engineering principles. Many of things we've actually been doing for the industry quite some time, but it's a good way to think about it. But it also is allowing us to kind of think about how would we apply the technology, which is kind of that's not quite as simple as just go buy an SST or a UPS and just kind of plug it in and it all works. So that's the game, and this white paper talks about this a little bit more. Let's go down this a little bit further, and I want to talk specifically around the rollout of 800 volt DC, particularly as we, and I think everybody here, including NVIDIA, I know Mike too from NVIDIA this morning talked about the phasing of these systems, is that there are clearly some phases that go on in the space, but it's not, as much as I love to talk about data centers and the physical side of it, remember, it is not about the physical data center. It is actually about the compute. The driver for 800 volts, the driver for moving to a higher voltage is because of the need to get more power into a single rack. That's what we talk about, the power in the megawatt era. It's kind of a euphemism. We actually will see 1 megawatt racks, but even above 350, 400 kilowatts, you will have the need to switch to this other voltage, which we'll talk about more about, but it really is around how to get the compute to be run more effectively and efficiency. Always bear that in mind, and it is not around on a more efficient, it is a little bit more efficient power delivery, but the load is really what matters. And when that load emerges, you have to think about these systems as well, which is, by the way, about the holistic thinking as I talked about earlier. So look, the fundamental challenge that we're facing here is that, next generation AI rack densities really are changing everything. If you think about today's architecture, anything that's in the, say, 100 kilowatts plus is built off of an OCP type architecture that really has a 54 volt bus running down the back with power shelves top and bottom with compute in the middle. It is a very effective and efficient way of delivering things, but it hits its limits. You get to the point where there's just the power space, the bus bars just get so big and bulky, there's not enough room for compute, which is the moneymaker, just to be clear. That's why we have to kind of drive that dimension towards this space. So there's just too much congestion. That valuable use space is getting taken up. Therefore, when you get up to higher rack densities levels, there are two things that the industry is doing to start with. Actually, in general, not even to start with, is when you get up above those levels, what you really want to do is you want to do two things at once. One is you want to take as much of the power and cabling out of the compute rack as possible. And the second is you want to increase the voltage. If I double the voltage, I have the current and I reduce conductors by at least 4x It depends if you want to cool them or not, and that really is kind of the value. You start resaving space and space. And this is where you get to this notion of a power rack. You take all that power stuff, you move it to a rack right next to you that has all the power conversion. You just bring back the bare minimum 800-volt cables to really free up that space in that rack. That's the motivation for all 800-volt IT racks. And the first step is to move it out and maybe move it localized just to a power rack. So what does the future of compute look like? If you're just looking at what's the moneymaker, the compute side of the space, really what's left is a rack, a top and a bottom rack, two different styles. One is still 54-volt based, but now the input cabling is 800 volts, so it's much, much smaller. We really are pushing the boundaries of power conversion to then power, probably up to around 800 kilowatts, depends if it's redundant or not in those dimensions. But the idea is that still can now push well above 400 kilowatts without a drastic change into the basic structure of the compute rack, but still requires 800 volts coming in. That's first one. The second is, look, even that 48-volt bus bar is stressing out. So the next step there is to do 800 volts distribution, not just coming into the rack with small cables, but actually internal to the rack as well. You'll hear NVIDIA talk about Kyber and those areas. It's built on that bottom architecture. So now those things on the right are really what has to be powered. Those are both 800 volt native racks and coming into them, and then but how they use them internally is a little bit different in that space. So that's where the world is going, and that's what we have to figure out how to power. The first step is to power it locally. And then as you get to scale, and we'll talk about what that means, is that you want to do that centrally. So first, locally, what we see here on the left is kind of rack level, where you basically have cluster of a power rack next to or near to an IT rack. And right now I'm showing a 1-to-1 ratio where you bring a lot of AC power, but to a power rack that's meant to take it, and you bring over to the compute rack DC cablings at 800 volt DC in that space. But that still takes up floor space. And the idea is that that's a valuable floor space. You want to change from that. So the idea is that you really want to do is you want to, at some point, if that's all the racks you're doing, you want to pull that back into a centralized approach such that now you're distributing 800 volts DC across your whole data center. Now that, of course, brings additional challenges because now you have to think about distributing DC, protection. All those schemes come more heavily into play. But that's where the industry is clearly going in phases, from localized architecture, and again, this is a very common architecture that you see emerging from Meta, Google, and NVIDIA for sure in that space. There's even clusters of taking clusters of four of those power racks together to power multiple racks as well, but all localized. The data center is still fundamentally AC. Centralized, think of it as the data center is fundamentally a DC data center in that space. And the driver here is really about, when you go to this, you get three values. You get the ability to kind of scale out at scale because they do not have any more power racks. You get greater power throughput, which is more power per cable or per busway. And because it's more centralized, it's much easier to do sort of grid direction and new integration techniques for grids, for on-site prem power, because you have fewer things to coordinate in that space. So all those are three values that emerge from a centralized DC approach. But as we've said, it's going to be phased. Not all data centers will have the same structure. I know that this slide is a little bit hard to read because everyone has an eye chart of the different architectures. What you see is if you can pick up the blue to the right, that's the increasing realm of DC, 800 volt DC that kind of is in each architecture overall. So the first is localized DC. When you're delivering power in 1 to 1.2 megawatt chunks, you localize approach, which is about these power racks or clusters of power racks. The middle actually has a lot of variation. And by the way, that first one's going to be deployed late 26, 27 for sure. The middle one is when you're delivering fundamental DC power, but in bigger blocks. Probably the 2 to 4 megawatt, closer to the 4 to 5 megawatt blocks are rare, but in different forms. Some are just kind of like, call it a DC UPS. You rip out an ACBS and you put a DC converter in there. Some are more around using well-known, ruggedized, very small, compact converters tied into standard medium voltage transformers. And some are using SSTs in that space. But the key is that the block size is around 5 megawatts. That's probably the 28 scaling factor for centralized. And then the last approach is where we do see blocks getting bigger. Could be as big as 12, could be as small as 8. It really is varying the space, but those block sizes will be a little bit future oriented for very large scale sales. Probably not until the 2020, late 29 plus horizon in that space. So again, it's not a single architecture. It is a portfolio of different architectures based on scale. Call it 27, 28, 29 plus, and then 29 future, all with a little bit different technologies, not because we like variation, but different starting points, different needs in that space. This is the portfolio that we see as the lineup, very similar to how NVIDIA talks about this as well, and I'm sure everybody in the market talks about this. So this should be new news, but I do want to be clear that when we think about age-interval DC, it does require thinking holistically around how all of this ties together. At Schneider Electric, we too think about this as a portfolio. And the idea is that it's not a single product. Our converter portfolio starts with power racks. The next coming out in 20 is a mix of low voltage, high density bidirectional rectifiers that take 400 or 408 volts DC. We combine that sometimes with a medium voltage transformer to bring 34.5 or 22 kV in and have a very robust, rugged conversion. And then at 10 kV or 13.8 kV, we actually are deploying or will be deploying, we have them going on right in other regions, SST technology as well. Again, not a one size fits all, but a full portfolio at that 5 megawatt range. The next scale is we call it the big boy. This gets up into that 10 to 12 megawatt range. That will almost always be SST technology because it gets too big if you're doing other types of technology as well. Plus, it gives a market to mature. This is what the industry, and I can certainly say this is what Schneider is doing to solve that run dense problem, particularly when you get into that space. It's not about a single SST or a single power rack. It does require a portfolio in that space. Now, what does it actually mean? It means that, as I talked about this, is that the meaning is not just around the conversion. I love to talk about converters. The industry loves to talk about converters, but do not forget about distribution and protection. Those are all being developed simultaneously with this. Codes and standards via OCP are driving through that space as well. All of that stuff is necessary to support the holistic view of these data centers. So while I don't have a lot of time to dig down those paths, the white paper does go down those paths and talks about the role of, there's a lot that we can do with mechanical circuit breakers, DC rated, electromechanical circuit breakers, plus combinations of hybrid and solid state breakers to make sure this can scale at speed in that space as well. So that's another reminder that we talk a lot about principle 1, principle 2, and 3 are equally important, as well as 4 and 5 in that space. So because of that, I do want to lay out the fact that I would love to talk for you for the next hour, but I know that this is 3 minutes. Let's not go for another hour to talk about all these things. So what we've done is we've created the white paper that talks about how these various elements think holistically around how you build at the scale and speed, whether it be how to manage AI load smoothing, if you're building retrofit versus greenfield, what happens if you're an existing colo and somebody wants to deploy an MGX 800 rack, how would you approach that? The role of where you want to make transitions from medium voltage to low voltage. Availability is a key decision factor, particularly if you get a lot of these IT racks, they're 4 makes 3, block redundancy, but you have to think about how you deploy that all the way back, and the role of storage. All these topics are well covered, at least at a depth level that is not too complex to understand, but also allows us to think more clearly around kind of where we actually have to evolve in this space. And because I love challenges, what I really want you to do is I would love for you to read and look at this white paper. I love to hear comments around what you think. Are we on the right track? Are we not on the right track? Think about it as the industry and also as Schneider Electric, as we are trying to lead this mission to build AI data centers at scale, efficiently and effectively for everybody in this space. So with that, I really appreciate your time and attention. Look forward to hearing and enjoying the rest of your evening, which I think will be exciting. And thank you very much for your time and attention.